Welcome to Academic Diaries class. Today we're going to be treating determination of the coefficients of viscosity using Stokes' law. So Stokes' law simply states that the viscous force or you say the resistance to the flow of fluids is directly proportional to three things. So it's directly proportional to three things, and those three things are coefficient of viscosity, velocity of sphere, or you say terminal velocity, and radius of the sphere. So this is his rule. So he now pulled out 4 pi. That is from 4 pi r square, which is radius of a square. He just pulled this out because this one is already directly to the radius only. So he put out 4 pi. And then the three things, he said half of this, half of this, half of this. That gives me 3 over 2. So times 3 over 2. This is going to be 12 pi over 2. So that is 6 pi. So 6 pi here is the constant k. So when you do it, you now see that varying directly, you now see that that is law, that is viscous force, viscosity. Viscous force here is viscosity. Is directly proportional to any coefficient of viscosity, V and R, then with the 6 pi. So this is Stokes' law on viscosity. So why I not put V here is because there's already V for velocity. So there you have it. So in doing the experiment, he put up a glass jar, cylindrical jar. In this cylindrical jar, you impute a sphere of known density, and the fluid we use here will be any fluid that has high viscosity. It cannot be water, because if it's water, the minute you put this thing here, it will go inside immediately. So, and you need to note that one of the procedures is that one, the sphere's density, or the rho of the sphere, must be greater than the rho of the fluid. And two, the fluid used must have low velocity. Number three, the fluid must be laminar. It must be flowing straight, not turbulent. That is, not be turbulent. So these are some of the procedures that comes to mind. So when you've done this, before you put this thing that I put here, you come and mark out any point at all. Mark out any points here, call it M1. That is with your meter rule, mark out M1. Then mark out any points down, M2. Now, before you even put this sphere of known density, you need to know that the sphere, you measure the sphere, one of the procedures again, you measure the sphere's diameter. Measure the sphere's diameter with micrometer screw gauge, and you measure this particular cylindrical jar that is very big. You measure the external and internal diameter using vernier caliper. So when you've done this, you now come before you even put this sphere of known density. So another rule is that the density must be known. The density. So in this case, he used castor oil. We are using castor oil. So the densities of sphere must be known. Okay, if it's already known, that means this one should be greater. So because if the sphere's density is not greater than that of the fluid, it can't enter inside. It will just float. If they are equal, it will just float. So the density of the sphere has to be greater so that it can enter inside. So it can move from M1 to M2, possibly sink. But the sinking is not what we're checking. So before you do this, you come, get your meter rule. Using your meter rule, get the distance from M1 to M2. This is S, which is also the same thing as H. It can also be the same thing in some cases as A to B, depending on what you mark that, or you say M1 to M2. So when you've done this now, the way you did the practical, you now come. By the time you put this ball, let's say all these things are fluids, the castor oil, by the time you put it, it moves from here, and as it's coming, the minute it gets to this point, you on your stopwatch. So you on your stopwatch, and it will move. You'll be checking the time. So the minute it gets to this point, you stop yours. You off your stopwatch. So you take it. So if, for example, you have something of density 70 kilogram per meter cube, and it has 7 seconds. If you put the one of density 80 kilogram per meter cube, definitely the time it will take will be lesser. So it can be maybe 5 seconds, because the denser, if it's denser, it means it has more mass. So it's more like the amount of how heavy something is. So I made the example in class using foam and stone. If I put stone inside 25 liter and foam inside 25 liter, the stone will feel heavier because it has more density. So I said if it has more density, this FEV, the more dense one that you put, because you'll be trying the experiment, you'll do it with so many of the spheres. So the ones that have higher density will tend to sink or enter this, run through from here to here faster. And you put this in a vicious flow so that you are checking it, the velocity will be slow. So when you are done with this, you will notice that for this thing to enter inside, as it's entering inside, the weight W is taking it down, mg. But as it's entering, according to Archimedes' principle, the fluid itself will tend to displace an amount of water that is equals to the amount, or should I say the mass of this particular sphere. And anything water talks about volume as well. So the mass and volume. So the mass and volume of fluid will be equal to the mass and volume of sphere. Reason being that Archimedes' principle states that the upthrust, that is the force exerted upward when something is immersed in a fluid, is directly proportional to the amount, or should I say to the weight of, or to the mass and volume of that particular thing. So if I dip my hand inside water, the amount of water that will fall, like in a bucket filled with water, if I dip my hand inside, the amount of water that will leave that bucket is equal to the amount of mass or matter that my hand is having. So if I know this, it simply means that out of the 6 major things we look at when we are dealing with fluid, that is mass, volume, density. So we know in this case now upthrust, Then viscosity, yes. So in this measure, five things. We can talk about the radius, but sorry, we're talking about forces. So in this measure, and then weights, the six. So weights. So we're saying that whenever we're treating fluid or Archimedes principle, that these two are equal. This can never be equal. This one is not equal because if it's greater, the one with, if it's greater than the fluid, if it's greater than the fluid, if the density of whatever you are imputing, let's say sphere, is greater than the fluid, then it will try to move to sink. But if they are equal, it will just float. So you need to know that. So density can never be equal. So if I know that, we are not saying that if we do this practical, that when we do this practical, that up thrust, as this thing is going inside, up thrust U is going up. And because it's going down, the water itself is traveling down. You are pushing this water to go down, and as it's coming, like as it's compressed, sorry, no, I say water, God forbid, we can never, another procedure is that we can never use water. We can't use water. No water. We can't use water to do this experiment because water has low viscosity. If you put this, it will just travel fast. You will be able to know to what you're doing. So as you're putting this thing, the castor oil is being squeezed to come down. So as it's going this way, anytime something is trying to go this way, viscosity, friction is going this way. So you can see in this case, what you are displacing because of the weight that entered U, and then V now, which you present with F in this case because we already have velocity, is now up. So that is why we say that from stroke law, stroke now gave us that U plus V, that is F, is equals to weight, and this is weight of sphere. Upthrust is simply talking about weight of fluids, of fluid displaced. Then this one is FV, that is for viscosity. So if you do it, let's analyze this. You can now see that this is mg, that is mass of sphere, and g. Let me not talk about. Then for this one, upthrust is going to be m and g. But you need to know that this one is mass of fluid and then mass of sphere here. But you remember that mass of fluid and mass of sphere, they are equal. Then V self, viscosity, has already been given to us to be 6 pi coefficient of viscosity, V for velocity, R. So if I know this, and this V that you see here is what we call terminal velocity. That is the velocity. Velocity is s over time. So that time that movement, anything movement is also that movement from this end to this end. So you come and do V equals to s over t. That time you are checking. So come and do. We check my first video in that practical class. You see how we did this. So if I know this, that means that I will now remember that when I'm treating fluid, look at the 6 forces there. Both forces and the things happening, the things to take note of. So I remember that density is represented with rho and is equals to mass over volume. So which means that since I know mass, that they are equal, and I already know volume. What is volume? The volume of sphere, remember, volume of sphere will be equal to the volume of water displaced, and the volume of sphere is simply gotten by integrating area. So area of a sphere is 4 pi r square. So if I integrate this, you simply add 1 here, divide by the new power, which is 3. So 4 pi r cube all over 3. So this is the area. That means that this is the sentence saying I have rho equals to mass. The masses are the same. Mass of sphere, mass of water are the same. Volume of sphere and volume of this the same. So all over 4 pi r cube over 3. So if I choose to make mass subject of the formula, mass will now be equals to everything here times this. If you like be wanting me to do it slowly. So this times this, and I have 4 over 3 pi r cube rho. So rho This row now is what is different, that is density. So this one, when I'm talking about density of sphere, density of sphere, that means this will be carrying S. And when I'm talking about density of, and when I'm talking about, I don't want to do this in here. When I'm talking about density of fluid, it will now be equals to 4 over 3 pi r cube. That is, let's say I do m of sphere and m of fluid. They are equal. They are equal because the amount of matter that that sphere is containing is the amount of water it will displace. So, but the densities are different. So F. So this is the one that is not different. So if I know this, if I carry this thing now that I've done here and impute here, we are trying to determine, make this V subject of the formula, because that is the goal. That was, or should I say, that was what Stroke did. His experiment was based on the fact that the velocity, terminal velocity at that point, that at equilibrium, he said that at equilibrium, that there will be no movement, no acceleration. And yes, we know that at equilibrium, it means state of no movement, no torque, no net force and the rest. So, but he said that the terminal velocity, the creeping velocity there will be equals to something. So that is what we are trying to find. So let's now do up thrust, has to do with weight of fluid displaced. So let's put, that means that this mass now will be mass for fluid. So it will have this on it. So I will now have replace M here with what it is, 4 pi r cube rho F. 4 over 3 pi r cube rho F. Then times G, mass times G equals to this. So plus 6 pi viscosity VR is equals to, this is weight of the sphere and mass of the sphere nuclear. So 4 over 3 pi r cube rho S. So if you like, go and be writing your S and F big. You now come and forget to think F is part of it, which is wrong. So now, since it's V, this V I want to get, can just say, let me make everything a subject formula so that this will cross over. So I have 6 pi coefficient of VR. This is coefficient of viscosity, which is also called eta, equals to 4 over 3 pi r cube. We did this in class, but I don't know what my phone did, and I lost the whole thing. Everything here is mass. I lost the video, so I'm starting it from the beginning. Then G. So for everything here, then if this one crossover, if this crossover, minus 4 over 3. Sometimes you think I am too fast. That's because you want to do it once and get the whole thing. It's something you slow down. If you're serious about learning, you have to slow it down, take your time, replay it. I know people that want to understand. And then this here now, this thing that I have here now, is simply saying the same thing as saying 4 pi r cube rho S G minus 4 pi r cube rho F over 3. This is the same thing with this. It's the same thing. So I can now say is equals to 6 pi eta V R. Now see, since it's V I want to make subject of the formula, I can say cross multiply everything here so that it will cross over. And when it crosses over, I will now have 1 times this, so that this will now be the same thing as saying V is equals to 4 pi r cube rho S, density of sphere G minus 4 pi r cube, density of fluid all over. If this is coming down here to me, 6 times 3, 18 pi eta r. So this is now the same thing as saying V is equals to, let's say 4 pi r cube rho sg all over 18 pi eta r minus 4 pi r cube rho f all over 18 pi eta r is the same thing. So if that be the case, I continue this here. So that I now have v is equals to 4 here. Sorry, if I do 4 divided by 8, I'll have 1 and 4.5. I don't want to have decimal points, so I'll say 2 here, 2. Then all over 2 here, 9. Pi here, that is 2 here, 9. 2 here, 2. Pi here, pi here. Now, r here, 1. R here, 2. So I have r square. Then I have okay, I think that's all. So I have g, then this is eta, equation of viscosity here. So minus 2 here, 2, 2 here, 9, pi, cancel pi, r here, 1, r here, 2. So anything over 1 is that thing. So I now have 2r square. Remember, I'm having this one as well here, rho s. So I now have remember that, what are you doing, this man? Remember that everything here is having this g, having this g, having this g, so having this g. So I'm now having g rho f. Multiplication is distributive. I can do it moving anyhow. This is 9, this is eta. So if you see this now, because I already know this is terminal velocity, Vt will simply be equals to this. This is the final answer. But because I know that there is a way Stroke presented his equation, I can say let's factor out. I have 2, I have r square, I have 2, I have r square, I have g, I have g. So let me factor it out. 2r square g into density of sphere minus density of fluid all over 9n, 9n, 9n is the same thing. If this times this, you have this with this part. If this times this, you have this. So it's the same thing. So there you have it. So this is the formula for terminal velocity, and this is the same thing as saying s over t, or you say h over t is equals to 2r squared g, because velocity is the same thing as displacement over time. So whichever way. So if they ever ask you to compare it with equation of a straight line, everything here is y. And if maybe what you are doing, let me do it this way. If you check this is setting as saying Vt equals to, most times they tell you to plot a graph of v terminal velocity against r square. So this is setting as saying 2g rho s minus rho f or r square all over 9 eta. So everything here is your m equals to Vt. So this is y-axis, and this is your x. That means that plus 0, which means that anytime you are doing this practical, most of the time, your vertical intercepts will be equals to 0. Note that. That's what I have for you today. Thank you.